Yes, good evening, one and all. So I hope you can see the screen. So let us continue the topic. So yesterday we have discussed about this KVL and KCL. I hope you can see the pointer. Okay. So just we have gone through the statements of KCL and KVL. Just recalling the statements of these two. So let us start our lecture. Okay. So KCL. So Kirchhoff's current law, or you can call it as Kirchhoff's current law. That's up to you. So what does the KCL represents, or what does the KCL says? Okay, so incoming currents is equal to outgoing currents, right? So here, what about this? I'm so sorry, it is KVL. This is KVL. Okay, so here, coming to KVL, algebraic sum of all branch voltages around a closed path in a circuit is always zero at any instant of time. So just I have given I have written the complete statement in the previous lecture. Please go through the for that lecture, the session what I have taken before to this. Okay, so algebraic sum of all branch voltages around a closed path in a circuit is always zero at any instant of time. All right, so we'll start from this point. Okay, right. So here these are the three branches again. So I'll just recall the things. So what do you mean by branch? So it represents the path between two nodes. Path between two nodes. Minimum two nodes are required in order to call it as a branch. Okay, so that those branch elements may be resistor, inductor, capacitor, or maybe a voltage source, or maybe a current source. Okay, so for time being, just remember, don't just include the voltage dependent currents, like the independent sources, voltage dependent current source, current dependent voltage source, and vice versa. Okay, just limit up to here so that it will be easy for you to understand about the problem solving in KVL. So resistor, inductor, capacitor, voltage source, and current source. Right. So here there are three branches. So let it be one, let it be two, let it be three. Okay. So three branches are there, and there is a closed path. Okay. Here we can call it as the circuit is closed. So as per KVL, so what he says, algebraic sum of all branch voltages. Okay, so what are the branch voltages here for the branch one? So they have labeled as V1 is the voltage source, right? Okay, so algebraic sum of all branch voltages. So branch one is done, and next is about branch two. So that is V2, and next is about third branch. So they have given the voltage as V suffix 7. So let us continue the same. Okay, algebraic sum of all branch voltages is equal to 0. Just I have added all those things. Okay, here another thing we have to be careful that what about the sign conventions, or what about the polarities? Suppose if you take this direction, let me change the color. Suppose this direction I have considered, and it is not mandatory that we have to consider only this direction. Okay, you may consider the opposite as well. Okay, so anything is possible, fine. So then what about the polarity of this V1, whether we have to go with plus V1 or minus V1? Let us see. Suppose if we are considering this direction, so then what is happening here in this particular branch element, or in this particular branch? Again, so just don't think that it is just a box, just it is a any element. So it may be any element, it may be a resistor, inductor, capacitor, or many combination. Anything is possible here. Okay, for that particular element. Okay, so whether we have to use plus polarity or minus polarity. So if you see here, it is starting from lower potential to higher potential, right? So see, from minus to plus. So we can call it as from lower end to higher end, or from lower potential to higher potential it is moving. So I can call it as potential rise. then I can go for plus V1. Okay, next coming for this branch 2. So it is leaving this and it is entering, the current is entering to this next branch, right? So it is from minus to plus. Okay, so again there is a potential rise, you can go for plus. Next, this branch is done. Next it is entering to branch 3, which we call it as the voltage as V suffix 7. Okay, done. So then what about the sign convention here? It is going from plus to minus, so this is the direction. So then it is a potential drop. Okay, so that is why the polarity is minus V7. So again I'm writing the same equation here. So plus V1 I can write it as V1, next plus V2 minus V7 is equal to 0. So this is as per KVL. So algebraic sum of all branch voltages around a closed path in a circuit is always 0 at any instant of time. So this is how we are going to simulate this circuit with the help of KVL. Okay. So once we are moving to the problems, then I can say that, so you have some more information about this KVL, how to solve the problems in KVL. Okay, but as of now, so just consider these fundamental things. Okay, next we will see with the KCL. Okay, so here this is the node. So how many again? Here three, there are 3 branches. So let it be. So this is a branch 1. Just a second. Yes. So this is branch 1. So here again, if you see the direction of the current here, so it is mentioned as incoming current. So if you consider this as a node, again, what do you mean by a node here? Node combining 2 or more branches. Okay, so the point where the combination of 2 or more branches appear, okay, or occur. Okay, so this is a point of contact where the number of branches are being connected. Okay, so again, so there is no difference between this point and this line. Okay, all are connected to the same point. Okay, so done. So this is one branch, this is another branch, and this is another. Okay, and they have mentioned the direction of current. Okay, and they have given the value as I2, I4, I3, I5 respectively. Okay, so here as per KCL, incoming currents is equal to outgoing currents, right? So let us consider this point as X. Okay, so apply KCL at point X. Apply KCL at X. So then what is the incoming currents? So here for this particular point X, so I2 is the incoming current. So I can write it as I2. So incoming current. And for this point X, what is the incoming here? I5. So just I can add this current I5. And for this point X, what are the, is there any other incoming currents? No. So, and what about the remaining I3 and I4? Those are leaving the node. Okay, so those are the outgoing one. So which is equal to, as per KCL, so I3 plus I4. So this is the equation. So that means sum of incoming currents must be equal to sum of outgoing currents. Okay, so like the appliances, right? So whatever the current entering to that particular appliances, that should be leaving with the, and it is going to enter with the other appliances. Okay, so that we'll see later on the practical situations and all. So this is about the fundamental information of KVL and KCL. So especially this is something very easy for us, whereas coming for KVL, so we have to remember the polarities, whether we are writing positive or negative. If positive, why we are writing, if negative, why. So those things we need to recall, we need to analyze. Okay, sorry. Next, let us see a very simple problem here. So I'm not going for complex problems because we have not started with the parallel and series connection of circuit elements. Once it is done, then we can go in deep of the solving the problems. Just we see only the simple one. Okay, so this is a basic circuit. So here we can see a voltage source, so which is of 20 volts. The same circuit here also, just anything you can consider. Okay, and there is a resistor which is connected in series with this voltage source of 2 ohms. The value of this particular branch is 2 ohms. That means the resistor is there. Okay, here another branch which of 3 ohm resistor is connected. Okay, so here already in the problem itself they have mentioned the polarities, so that is okay. Then we have to follow the same polarities. If suppose the same circuit, see, let me draw here. Okay, suppose it is 2 ohms and it is 3 ohms and the voltage source of 20. So this is how the circuit will be. So they are not going to give any polarities, or they are not going to mention any current direction. This is how already they have mentioned. So like this also it is not expected. So just they simply ask you to solve the circuit and find out any parameter, like what is the power absorbed in this 2 ohm resistor, or what is the power absorbed in this 3 ohm resistor, or you can they can ask for what is the voltage across this 2 ohm resistor, or what is the voltage across this 3 ohm resistor, or they may ask you that what is the power absorbed in each and individual element, or maybe the whole circuit. So like this any possibilities may there. The thing is that they have not given any polarities and they have not mentioned the direction of current. If suppose the circuit is in this way, then what you have to do at the starting is, so you have to redraw the circuit. I'm just letting you know how to start with the problem. Okay, just as it is, draw the circuit and mention your polarities in this way: plus, minus, and plus and minus. So in this way, you need to mention your polarities and consider this direction of current. Okay, so this is the usual way of solving the problem. So, and again I'm letting you know that it is not mandatory to consider the direction of current in this way. So in this direction of also you can consider, in this direction of current also you can consider. Okay, but easiest way is that better we can start with the polarities mentioning in this way. Okay, and the direction of current is this. Okay, let it be current I. Okay, this is a very simple circuit. Okay, so let us go with this circuit. So that is figure A. So the extension of figure A is nothing but the figure B. So here they have included the direction of current. So that is the only difference. Okay, done. So how we need to start? As per KVL. So apply KVL for, or we can call it as apply KVL for loop 1, or since it is a single loop, so I can call it as a single loop here. So apply KVL for loop 1. So what does it mean? Algebraic sum of all branch voltages. The thing is that we have to combine all these voltage sources and we have to make equal it to 0. Okay. So first we'll start with this 20 volt voltage source. So already it is 20 volts. Okay. No need to write the units. 20 V in the sense V is volts and those are the units. So just simply you can write 20. Okay, and whether it is plus 20 or minus 20, so that we need to identify here. So it is starting from minus to plus, so there is a potential rise. Okay, so it is from lower end to higher end, or lower potential to higher potential, so then we can mention it as plus 20. Okay, next, what about the next element here? So 2 ohm resistor. So we don't know what is the exact voltage across this 2 ohm resistor. So what we need to do, they have already given. So you need to consider as V1 is the voltage across 2 ohm resistor. V1 is the voltage across 2 ohm resistor, and V2 is the voltage across 3 ohm resistor. So already they have mentioned V1 and V2. So directly you can apply the same. So voltage across 2 ohm resistor is V1. So that is V1. Whether it is plus V1 or minus V1, again we need to check the signs here. So it is starting from plus to minus. So then we have to write it as minus V1. Okay. Next, what about the next element? 3 ohm resistor. So again, if you see the polarities, it is going from minus to plus. Again, there is a potential rise. Okay, then it is plus V2 is equal to 0. So almost we have completed three elements. Okay, one is voltage source, two are the resistive elements. Okay, so algebraic sum of all branch voltages is equal to 0. So this equation is as per KVL. Right. So just make any note. If you have any doubts, just have a note somewhere. At the end of this class we can definitely give some clarity if you have any doubts on this. Okay, just make a note in somewhere. Okay, next, again I can rewrite this equation as, so 20 minus v1 plus v2 is equal to 0. So v1 minus v2 minus 20 is equal to 0. Let it be equation 1. Okay, so this is how the KVL, so I mean the equation is solved as per the KVL. Okay, so the same steps I have given. So what they have mentioned, find out the voltages across, sorry, in the problem they have mentioned that voltages across V1 and V2. So the problem is that we need to find out what is the value of V1 and what is the value of V2. Okay, so we know that what is the voltage across this uh, resistor, voltage across this resistor or any resistor, V equal to, so that is V equal to I into R. Okay, so this is the applied voltage and this is the current flowing through the resistor into the resistor value. Okay, so that is the value here. Since the current what I have mentioned here is I. Okay, so then what will be the value of V1? So V1 equal to, so I into, what is the value of R here? 2 ohms. Okay, so I hope you can understand this, or else I'll just extend this the same thing. So V1 is the voltage across the 2 ohm resistor, and what is the value of V1? V1 equal to current flowing through this resistor. Already it is mentioned as I. So here you can see, right, and the resistor value. Okay, here the resistor value is 2. So then it becomes V1 equal to 2 into I. And what about this 2 ohm, 3 ohm resistor? Let me use the other. Yes. What about this V2? So V2 equal to I into R. Okay. So again, what is the value of this R? 3. So V2 equal to I into 3. So V2 equal to 3 into I. Okay. So let it be equation 2. So these two I can combinedly say it as equation 2 and this is equation 1. So what happens when I substitute this here? What happens when I substitute 2 in 1? So substitute 2, equation 2 in 1. So then it becomes, what is the value of V1? 2I minus 3I minus 20 is equal to 0. Okay. So then it becomes, so minus I or I equal to, so I think somewhere we have done mistake. Let me check. So V1 minus V2, V1 minus V2 minus 20 is equal to 0. Done. Okay. Okay then. Right. So it may be I minus 20 is equal to 0. So I equal to minus 20 approximately. So let me check whether I have done somewhere I have done wrong. So 2I, so polarity 2I plus 3I. So it is 2I and 3I, it is correct. Why they have considered it is no. So you can just follow this. Okay. So this is 20 amps, no issue. If it is mistake, we can check it later, right? So it is found that I equal to 20 amps. Okay. Then you can substitute here and you can find out V1 and V2. Okay. So what is I here? 20 into 2, and here it is 20 into 3. No. Let me solve it again. So V1 equal to 2I, so V2 equal to minus 3I. Done. So it is minus 20. No. So it has to start with plus 20 minus V1 plus V2. It is also fine. So it is 20 plus 20 minus V1 minus, sorry, it is plus, it since it is at a potential rise, minus to plus V2 equal to 0. So I can write it as minus V1 plus V2 plus 20 equal to 0. Done. Okay. So here, what is the value of V1? V1 equal to I into R. So which is equal to I into the R value is 2. So which is equal to 2I. Okay. Next, what about this V2? V2 equal to, so I into R. So which is equal to I into 3. So that is 3I. Just we need to substitute this. Okay. So V1 equal to minus 2I plus 3I plus 20 equal to 0. Okay. So it becomes I plus 20 equal to 0. I equal to minus 20. So this is right. This is fine. Okay. Just you can substitute this value. So and again it is not becoming 0. So let me check with this problem what is the wrong here. So it is 8 and it is 12. Okay. So just I'll give you clarity. So next we'll go with the KCL. Okay. Next. So coming for this KCL, so obtain the currents I1 and I2. Okay. So here this is node A and this is node B. So here two nodes they have mentioned. So they have asked for I1 and I2. So what is I1 here? So this is I1 and this is I2. Okay. So considering node A, between node A and B. Okay. So these two are same because there is no particular any branch or any current was mentioned. So obviously these two branches remain same. Okay. So then for these two, what are the incoming currents? So this is an incoming current, and 7 amps is also an incoming current, and I1 is also an incoming current. Yeah. Okay. So this is incoming. Just a second. Okay, so this is incoming and this is outgoing. This is incoming, and 7 amps is also an incoming, and I1 is also incoming. Okay, so then it becomes 2. 2 is incoming here, 7 is also incoming here, and I1. So I1 is also incoming, which is equal to 3 amps. So from this easily we can find out. So 9, so 3 by 9, sorry, uh, yeah, this is 9 plus I1 equal to 3. So I1 equal to 3 minus 9. So that is minus 6 amps. Already it is mentioned. Okay. So here minus 6 amps in the sense the direction of current what is mentioned here is not the exact one. It may be the outgoing current. So the magnitude remains same. If the current is showing it as plus or minus, then only the direction is representing. Okay. So we have found that I1 is 6 amps as per the KCL applied between the nodes A and B. So actually these two nodes are same. Okay. If suppose if there is any element here, okay, so it may be 1 amp or some value may be there, then you have to consider these nodes as separate. You cannot combine these two, A and B. Then A you have to consider it separately and B you need to consider it separately. Okay. Next, coming for this I2, we need to find out I2. Okay, so we need to find out I2. So see, between C and D, so apply KCL at C and D. So these 2 points are same again. Let us see the incoming current for this C and D. So 4 amps is incoming and 1 amp is outgoing, and for this C again 1 amp, sorry, I1 is outgoing here, and for this I2, so I2 is also outgoing. Okay, done. So then what we can write here, so 4, because 4 is an incoming, and almost all are right, outgoing, right, incoming. So this is also outgoing. 4 equal to, so outgoing is I1 plus I2 plus 1. Okay, already we have found that I1 is minus 6. So you can substitute just simply I1 is minus 6 plus I2 plus 1. Okay, so then it becomes 9. So I2 equal to 4 plus 6 minus 1. Okay, so that is 9 amps. So also C and D comprises single node. So S, the value is 9 amps. Okay, so this is how we are going to solve the KCL here. So let me solve one simple problem here. Let me go with the another example. Since I'm not convinced with this problem, so let me take another example as well. Yes. So this is a 10 volts. Okay. So this is 2 ohms and this is 3 ohms and this is 4 ohms. Okay, so this is what the circuit. So I want to find out the current flowing through this circuit. Okay, so then what will be the KCL equation? So what will be the equation of the circuit as per KVL? As per KVL, so it will be 10. So 10 minus, so here I am going to give the polarities as plus and minus. Here it is plus and minus. This is as per my convenience. You can use it in reverse direction also, no issues. Okay, so this is 10 And what about this? There is a potential drop, so then it will be uh, minus 2 into I. So I don't know about I, because how these equations appear, it is I into R. Okay, so it is the voltage across the 2 ohm resistor, that is IR. So I we don't know, so just simply I'm writing it as I, and the value of R is 2. And coming for this 3 ohms, it is again, it is starting from plus and it is leaving from minus. So that is minus 3 into again I. Next minus 4 into I is equal to 0. So here you may ask me that, sir, why this I is remaining same for this entire elements? In series the circuit, in series circuit the current is same. Okay, so that is the reason the current I am writing it as I for all the resistors. Since when the elements are connected in series, whatever may be the elements, either it may be a resistor, inductor, or capacitor. Okay, I mean the passive elements. Okay, so the current remains same here. In case of parallel, the voltage will be same. So that is the reason all of your appliances, when it is connected to a voltage, so voltage remains same. Like for example, AC is connected at 240 volts. Even for an LED lamp, it is connected with a 240 volts. So the voltage remains same, but the individual current drawn by that particular appliances is different. Okay, since it is a parallel circuit. Okay, next, so I can solve this equation as 10 minus 5 minus 9 I is equal to 0. So I equal to, so 10 equal to 9I. So I equal to 10 by 9. So this is the current drawn by this circuit. Okay, so this is how we need to solve the KVL. So let me go for this series and parallel connection of circuit elements. Okay, so see again. So yes. So here, this is the way of representation. So don't get confused all the time. Don't need to write it as this resistor symbol. Okay. So any of these things I can use. Just I can represent in a single box. Okay. So consider this as a resistor 1, resistor 2, and resistor 3. So as per the KVL, so here I need to find out when the resistor is connected in series. Okay. So what will be the equivalent resistance? So this is I into R1, this is I into R2, if it is I into R3. If suppose all these are resistive elements. Okay, so as per KVL, the algebraic sum of all branch voltages is equal to 0. So that is what it was written. P equal to the total voltage applied across these resistors, okay, is equal to V1 plus V2 plus V3. Okay, so this is what we have mentioned here. Okay, so I into R1 plus I into R2 plus I into R3. So again I is remaining same because it is a series circuit. Then what is R equivalent? So R equivalent equal to, so R1 plus R2 plus R3, like this and so on. How many resistors you have connected in series? If suppose there are n number of resistors are connected in series, then the equivalent is like this. Okay, if suppose only two resistors are connected in series, okay, then what will be the equivalent? R1 plus R2. Next, we go with the series connected inductors. Okay, so let me draw. This is a very simple thing, so no need to think much about this. So the thing we need to remember that what is the equivalent value. So that we need to concentrate. Suppose two inductors, let it be inductor L1 and L2. So this will be the L equivalent. Okay. So we want to find out what is the equivalent if two elements, that is the inductor, are connected in series. Okay. So then we can write it as, so what is the voltage applied across this inductor? V1 equal to L1 into di by dt, and again I remains same. Okay, so what will be the V2? So L2 into di by dt. What is the voltage applied across this equivalent? So V equivalent equal to L equivalent into di by dt as per KVL again. So this is made equal to these values. So V equivalent equal to V1 plus V2. So then L equivalent into di by dt is equal to L1 into di by dt plus L2 into di by dt. So then this di by dt gets cancelled here if I make it as a common. So then what is the equivalent? L1 plus L2. Okay, so this is how, if you connect n number of inductors are connected in series, then uh, the value is L1 plus L2 and so on Ln. In the same way, I can go for capacitors. Okay, if two capacitors, just for time being, I'm considering two capacitors. Okay, and this will be the equivalent capacitance. Okay, so what is the voltage applied across this equivalent capacitor? So let it be, so this is V1 and voltage applied across this capacitor is V2 and the equivalent capacitance voltage is V equivalent. So as per KVL, V equivalent equal to V1 plus V2. Okay, so what is the voltage applied across this equivalent resistance? 1 by C equivalent integral I dt. Okay, and what is the voltage applied across this C1? So 1 by C1 integral I dt, since the current remains same for the series elements. Okay, and 1 by C2 integral I dt. So again the same thing, if you cancel out these terms, then what it becomes? 1 by C equivalent equal to 1 by C1 plus 1 by C2. So how I can write it as 1 by C equivalent equal to C2 plus C1 by C1 C2 if I go for LCM. Okay, so then C equivalent becomes C1 C2 by C1 plus C2. So this is the equivalent value of capacitor when two capacitors are connected in series. So just I would like to highlight the thing is that when two resistors are connected in parallel, sorry, when two resistors are connected in series, we have to go for summation. Just we can add the resistor value of those two elements, that is R1 plus R2. Next, if suppose two inductors are connected in series, we can go for L1 plus L2. When two capacitors are connected in series, what is the equivalent here? C1 C2 by C1 plus C2. Okay, so in the same way, when the resistors are connected in parallel, so then applying KCL here. So it is better to apply KCL in the parallel circuits. Okay, then what happens? You can cross check with this derivation. So the same way what I have solved for these series circuits. Okay, so if two resistors are connected in parallel, okay, if two resistors are connected in parallel, so this is R1 and R2. And also you may ask me, sir, how can we I mean, how can we identify that so these two are in parallel? So the thing is that this is the current entering here and it is going to differentiate, or it is going to divert, or it is going to split into these two elements. Okay, the current what is entering for this element is different for this element. Okay, and whereas for series, the incoming of current of one particular element is equal to the, sorry, suppose this is R1 and R2. Okay, so for this R1 the incoming current is I, and for this R1 outgoing current is again I, and which is equal to the incoming current of R2. So one element, so the input current of one element is equal to the output current of the another element. So the thing is that it is flowing through the same direction. Okay, here there is no any tap, or is there any kind of connection? Nothing is there. So the current is not bifurcated here. Okay, so the current is not going to split here. So that is the reason between this series connection and parallel connection. In the easiest way, I'm trying to say it for you for remembrance. Okay, and what about this parallel here? This is the main current, and for these two currents, for these two elements, the current is splitted into two halves. Let it be, this is I by 2 and this is I by 2. So this is called as the parallel connection. Okay, so for resistors connected in parallel, so what is the equivalent? R1 R2 by R1 plus R2. In the same way, when two inductors are connected in parallel, so it will be L1 and L2. So then it becomes L1 L2 by L1 plus L2. If suppose two capacitors are connected in parallel. Okay, this is also a parallel connection. Okay, so then what will be the equivalent? It will be C1 plus C2. So that we need to notify. Okay, so just I can give you in the next class about the derivation of this, how we are getting these values C1 plus C2, why we have to add it here, why we are going for cross multiplication. So that I will try to give you the derivation in the next session. So that's all about for today.